Now let us consider another example in which the signal x of n is given as 1 by 2 whole power n u of n minus 3 into 1 by 3 whole power n u of minus n minus 1. Here the ROC, the jet transform of 1 by 2 whole power n u of n is 1 by 1 minus 1 by 2 z inverse along with the ROC of mod z greater than half, and the jet transform of minus 1 by 3 whole power n u of minus n minus 1 is 1 by 1 minus 1 by 3 z inverse with a jet transform of mod z less than 1 by 3. Here please note that the intersection of the ROC is mod z greater than half and mod z less than 1 by 3 is pi. So the jet transform of x of n doesn't exist. So if the ROCs of the signals don't overlap, then the jet transform of the cumulative signal doesn't exist. Now let us consider another example as per which the signal x of n is given as 1 by 3 whole power n u of n minus 1 by 2 whole power n u of minus n minus 1. Here, for finding the jet transform of x of n, we have to find the jet transform of the individual signals. So the jet transform of 1 by 3 whole power n u of n is 1 minus 1 by 3 z inverse with an ROC of mod z greater than 1 by 3, and the jet transform of minus 1 by 2 whole power n u of minus n minus 1 is 1 by 1 minus 1 by 2 z inverse, and the ROC is mod z less than half. So here the ROC is mod z greater than 1 by 3 and mod z less than 1 by 2 overlap. So the jet transform of x of n doesn't exists. So from this the jet transform of x of n can be written as 1 by 1 minus 1 by 3 z inverse plus 1 by 1 minus 1 by 2 z inverse. And here we see that upon simplification there is no pole zero cancellation. So because of which the ROC of jet transform of x of n is 1 by 3 less than mod z less than half. So from this we can say that given the linear combination of two signals, the jet transform of x of n exists if ROC, which is intersection of ROCs of individual signals is not equal to 5, and also if there is no pole zero cancellation, the ROC is superset of R1 intersection R2. If if there is no pole zero cancellation, ROC is equal to R1 intersection R2. If there is no pole zero cancellation, ROC is superset of R1 int sorry if there is no pole zero cancellation, ROC is equal to R1 intersection R2. If there is a pole zero cancellation, ROC is superset of R1 intersection R2. Now let us consider another property of the jet transform, which is time shifting, as per which if x of n minus n naught is a delayed or advanced version of x of n, jet transform of x of n minus n naught is given as z power minus n naught x of z, and the ROC of z power minus n naught x of z would be r minus 0 or infinity. That is, if n naught is greater than 0, ROC is complete or except 0. If n naught is less than 0, the ROC is complete or except infinity. So from this we see that x of n minus n naught will have a z transform of z power minus n naught x of z, and depending on the sign of n naught, that is positive or negative, the ROC includes either ROC may exclude either 0 or infinity. Now let us consider an example as per which we need to find the z transform of 1 by 2 whole power n minus 3 u of n minus 3. We know that the z transform of 1 by 2 whole power n u of n is equal to 1 by 1 minus 1 by 2 z inverse with the ROC as mod z greater than half. Now, for finding the z transform of 1 by 2 whole power n minus 3 u of n minus 3, from the given property, we can write that z transform of 1 by 2 whole power n minus 3 u of n minus 3 is equal to z power minus 3 divided by 1 minus 1 by 2 z inverse, and the ROC would be mod z greater than half, as he n naught is greater than 0, which is 3 now. The ROC should exclude 0, which was already excluded in the original ROC of mod z greater than half. So from this we can say that the z transform is z power minus 3 divided by 1 minus half z inverse with ROC as mod z greater than half. Now let us look into another property as per which a power n into x of n has a z transform of x of z by a with the ROC of mod a multiplied by r. That is, if r1 less than mod z less than r2 is the ROC of x of n, x of z, then the new ROC would be mod a multiplied by r1 less than mod z less than mod a multiplied by r2. So suppose mod a is greater than 1, then multiplication by a power n in time domain implies compressing the shrinking the of z transform in z domain. Similarly, if mod a is less than 1, multiplication by a power n is equivalent to expanding in z transform domain. Also, if a is equal to e power j omega naught, then z by a will be equal to r into e power j times omega minus omega naught. So multiplication by a power n, that is e power j omega naught n in time domain, is equivalent to frequency shift by omega naught. Now let us consider another property of Z transforms, that is differentiation in Z domain. That is, if Z transform of x of n is x of z along with an ROC of r, Z transform of n into x of n is z into d by minus z into d by dz of x of z, and the ROC would remain as r itself. So now let us Consider an example for the same. Suppose we need to find the jet transform of n into 1 by 2 whole power n u of n. We know that jet transform of 1 by 2 whole power n u of n is equal to 1 by 1 minus half z inverse, and the ROC is mod z greater than half. Now the jet transform of n into 1 by 2 whole power n u of n is equal to minus z multiplied by dz of 1 by 1 minus half z inverse, with the ROC as mod z greater than half. So upon simplifying the same, we get the z transform as shown, that is minus z multiplied by minus 1 divided by 1 minus half z inverse whole square multiplied by minus half multiplied by minus 1 z power minus 2. This upon simplification becomes half z inverse divided by 1 minus half z inverse whole square with ROC as mod z greater than half. From this we see that z transform of n into 1 by 2 whole power n u of n is equal to half z inverse divided by 1 minus half z inverse whole square with ROC as mod z greater than half. Now let us look into another property of Z transforms, that is conjugate property. As per the conjugate property, the Z transform of x star of n is equal to is x star of Z star, with ROC being R itself. So let us try to prove this. Let y of n is equal to x star of n, where star implies the conjugation operation. Then y of z is equal to sigma n equal to minus infinity to plus infinity y of n multiplied by z power minus n. This is further equal to sigma n equal to minus infinity to plus infinity x star of n multiplied by z power minus n. This can also be simplified as sigma n equal to minus infinity to plus infinity x star of n and z star of minus n whole star. This is because the double conjugation implies the z itself. So this can further be simplified as sigma n equal to minus infinity to plus infinity x star of n, sorry, x of n multiplied by z star of minus n as a whole star. So this is equal to x of z star whole star. So this is equal to x star z star. From this we see that the z transform of x star of n is equal to x star of z star. So this is the conjugation property. Now let us look into another property of z transforms, that is time reversal property. So as per this, the z transform of the signal x of minus n is given as x of 1 by z, with ROC being 1 by r. That is, if R1 less than mod z less than R2 is the ROC of x of z, then the new ROC would be 1 by R1 less than mod z less than 1 by R2. Sorry, 1 by R2 less than mod z less than 1 by R1. This corresponds to x of 1 by z. So this can also be proved as shown. For proving the same, let y of n is equal to x of minus n, then y of z is equal to sigma n equal to minus infinity to plus infinity x of minus n z power minus n. Upon substituting m is equal to minus n, we get sigma m equal to minus infinity to plus infinity x of m z power m. This can further be simplified as sigma m equal to minus infinity to plus infinity x of m multiplied by 1 by z whole power minus m. So this is equal to x of 1 by z. So from this we see that the z transform of the time reversed version is equal to x of 1 by z with ROC being 1 by r. Now let us consider another property of z transforms, that is initial value theorem. As per initial value theorem, x of 0, that is limit n tends to 0 x of n is equal to limit z tends to infinity x of z. If x of z is equal to p of z divided by q of z, for initial value theorem to be applied, the order of the numerator polynomial should be less than the order of the denominator polynomial. So from this we see that for initial value of theorem to be applied, the order of the numerator polynomial should be less than denominator polynomial. In which case, as per initial value theorem, x of 0 is equal to limit z tends to infinity x of z. Now let us check the same by example. Suppose let us consider a signal x of n that is equal to 1 by 2 whole power n u of n. From this we can see that x of 0 is equal to 1. Also by using the z transform of the same, x of z is equal to 1 by 1 minus half z inverse. Here the order of the numerator polynomial is less than the denominator polynomial. So the initial value theorem can be applied. So from this x of 0 is equal to limit z tends to infinity x of z. So this is equal to 1. So from this we see that the initial value theorem is indeed valid from the given example. Also please note that the initial value theorem is typically applied for causal sequences, and the example we have taken here is the causal sequence. Now let us look into the characterization of LTI system using the system function and ROC. Suppose there is an LTI system of impulse response h of n, then the z transform of the impulse response h of n is given as say h of z, and let the corresponding ROC be R. So based on the ROC of the LTI system, we can characterize the same for causality or anti-causality or non-causality or stability or memoryless properties. If the ROC includes unit circle, then the system is stable. If the ROC is outside a circle, then the system is causal. If the ROC is inside a circle, then the system is anti-causal, hence non-causal. If the ROC is a ring, then the system is non-causal as well. If the ROC is all Z, then the system is memoryless. Also, if the ROC includes unit circle, then it means that the impulse response h of n is absolutely summable. So the dtft of h of n exists. So now let us consider an impulse response of a LTI system, that is h of n is equal to 1 by 2 whole power n u of n. And we know that the system function of the LTI system is 1 by 1 minus half z inverse with ROC as mod z greater than half. So here we need to characterize the LTI system based on the given ROC. Here we see that the ROC is outside a circle. So from this we can say that the given system is causal. Also the ROC includes unit circle, that is mod z equal to 1. So the system is stable. We see that ROC is not all z. So the system has memory. As ROC includes unit circle, the system is stable. Hence, the DTFT of the sequence exists. So, given the region of convergence of a LTI of the system function of a LTI system, we can characterize the system for causality or non-causality or anti-causality, memoryless property, stability or existence of DTFT. Now let us consider another example as per which the system function of an LTI system is given as 1 by 1 minus 1 by 3 z inverse multiplied by 1 minus 2 z inverse. If the system is anti-causal and stable, find the ROC of h of z. The possible ROCs of h of z are mod z less than 1 by 3, 1 by 3 less than mod z less than 2, and mod z greater than 2. This is because ROCs are bounded by poles and shouldn't contain any poles. So in the case of first ROC, as ROC is inside a circle, the system is anti-causal and it doesn't include unit circle, so the system is unstable. And in the second case, 1 by 3 ROC is 1 by 3 less than mod z less than 2. In this case, ROC is a ring, so the system is non-causal. As it includes a unit circle, the system is stable. In the third case, the ROC is mod z greater than 2. In this case, the ROC is outside a circle, so the system is causal, and as it doesn't include a unit circle, the system is unstable. From this, we see that there is no ROC which corresponds to anti-causality and stability. From this, we can say that there is the given system with the required properties is not possible.